All right, so get ready because today we are going deep into some seriously head-scratching physics. We're talking entropy, time dilation,
Yes.
and gravity.
Oh, my favorite.
You know, the kind of stuff that really makes you question reality, the very fabric of reality.
Absolutely.
And guess what? We may be on the verge of a major shift in how we understand these fundamental concepts.
I think one of the things that really struck me going through all this research that you put together is that this recurring theme that time may not be this constant, unchanging backdrop to the universe.
Right.
Instead, it could be an emergent property, something that arises from deeper processes, and one of those is related to entropy.
So let's break this down for a second.
Okay.
We usually think of entropy as disorder, right?
Yeah.
Like how a tidy room just descends inevitably into chaos.
Right, exactly.
But how could that possibly be linked to time?
So think of it this way. Imagine a box, right?
Okay.
And it's filled with gas molecules, and they're all really neatly arranged at the beginning.
Okay.
That's a state of low entropy of very high order.
Low entropy, high order. Got it.
Now, as those molecules start bouncing around and spreading out, the entropy inside the box increases.
Okay.
And what researchers are suggesting is that time within that box, relative to an observer outside the box, would actually speed up slightly.
So you're saying the more disordered a system becomes,
Yeah.
the faster time flows within it.
That's the idea, yeah.
That's kind of counterintuitive.
It is, but it has some pretty fascinating implications.
Such as?
Well, think about this. It could explain why time seems to slow down near massive objects.
Okay.
We normally attribute that to gravity.
Yeah.
But what if it's actually due to the way that mass affects entropy?
Okay.
So think about it this way. Massive objects, they represent concentrated order
Right.
or low entropy in a chaotic universe.
So instead of mass directly causing time dilation, it's more like mass creates a region of slower time flow because of its low entropy.
Exactly. It kind of flips the conventional understanding on its head.
Yeah.
Suddenly, mass isn't the cause of time dilation, but a consequence of it. And this has the potential to kind of rewrite how we think about gravity itself.
Okay, now you've got my attention.
Good.
So how does this entropy-time connection actually relate to gravity?
Okay, so picture this. Imagine space-time as this giant, flexible sheet.
Okay.
A massive object, like a star,
Uh-huh.
would create a dip in that sheet because of its low entropy, its slower time flow.
Got it.
And just like if you rolled a marble across a sheet and there was a dip in it, other objects would naturally move towards that area.
Right.
That's what we experience as gravity.
Okay, so gravity isn't this force that's pulling things together, but rather objects responding to the shape of space-time, which is determined by these entropy gradients.
That's a good way to put it.
I like that. That's really interesting.
It's a pretty radical departure
Yeah.
from our traditional understanding of gravity, but it could explain some things that current theories struggle with.
Like what? Give me an example.
Well, let's take the formation of galaxies, for example.
Okay.
We know matter clumps together to form stars and galaxies,
Right.
but the current model of gravity doesn't fully explain why this clumping happens on such vast scales.
I see. So you're saying that this entropy-time connection could provide a better explanation for how the large-scale structure of the universe actually form.
Precisely. So picture a region of space, right?
Okay.
And it has slightly lower entropy than its surroundings.
Okay.
That region would experience slightly slower time flow, creating a sort of time well.
A time well, okay.
As matter drifts through space, it would naturally be drawn into these time wells, just like water flows downhill, right?
Okay, yeah.
This could explain how matter gradually accumulates over time to form stars, galaxies, and eventually even black holes.
Black holes, okay.
Yeah.
Which are very interesting.
Yeah.
This is really making me rethink everything I thought I knew about gravity. So where do black holes fit into this whole picture then?
Black holes are fascinating in this context. They really are.
Yeah.
They're often described as regions of maximum entropy,
Right.
where time essentially stops.
Okay.
If you look at it from this entropy time perspective, it makes sense.
Yeah.
Black holes are so dense, so tightly packed with matter, that their entropy reaches a maximum.
Right.
And time within them slows to crawl relative to the outside universe.
So in a way, black holes represent this ultimate victory of entropy.
Yeah.
The point where order collapses into chaos and time effectively ceases to exist.
It's certainly a compelling way to think about them.
It is. It is.
But the really interesting question is, what happens to the information that falls into a black hole?
Right, the information paradox.
Exactly.
Does it simply vanish, which would kind of violate one of the fundamental laws of physics?
Right.
Or is it somehow preserved?
Yeah. And we have some fascinating things to talk about with that.
Oh, can't wait.
But before we kind of get sucked into the abyss
Yeah.
of that conversation, let's step back and think about how this time dilation thing affects the quantum realm.
Right. This isn't just about stars and galaxies.
No.
Right.
It's much, much deeper than that.
This can have profound effects at the subatomic level, right?
Yeah.
Potentially influencing the behavior of quantum fields and giving rise to some truly bizarre phenomena.
Absolutely.
All right, lay some quantum weirdness on me.
Okay, are you ready?
I'm ready.
All right, so for starters, there's this thing called the Unruh effect.
Okay.
This mind-bending concept suggests that an observer accelerating through space would actually perceive a warm bath of particles in what should be completely empty space.
Wow, okay.
So it's like acceleration creates this kind of thermal mirage.
Interesting.
All thanks to how time dilation affects their perception of quantum fluctuations.
So just by moving really fast, you could essentially see particles popping in and out of existence.
That's the idea, yeah.
That's amazing. That's really wild.
It highlights how deeply intertwined acceleration, time dilation, and the quantum world really are.
Yeah, right.
But perhaps even more intriguing is the idea that time dilation itself might play a key role in the emergence of gravity.
Emergent gravity.
Yeah.
I'm sensing a connection here.
Yes.
But I'm not quite grasping it yet.
Okay, well, remember how we were talking about time flowing slower in regions of higher order?
Uh-huh.
What if those variations in time flow have a direct effect on the vacuum energy density of space itself?
Okay, back up for a second.
Right?
Vacuum energy.
Okay, so imagine the emptiest space you can possibly conceive of.
All right.
Completely devoid of matter.
Okay.
Even in that seemingly empty space, there's this background energy, and it's constantly fluctuating. And it's fluctuating with virtual particles popping in and out of existence.
Okay.
That's vacuum energy.
So even nothingness has energy.
Yeah, physics is wild, right?
Yeah. But I still don't see how this ties into gravity.
Okay, so some physicists believe that these time dilation gradients, which are caused by these variations in entropy,
Okay.
could actually create variations in that vacuum energy density. And those variations could then manifest as the curvature of space-time, which we experience as gravity.
Whoa, okay.
So instead of gravity being a fundamental force, it's more like a side effect of how entropy and time dilation shape the energy landscape of the universe.
Wow, that is a really, really fascinating idea.
It is.
It's a big idea.
It's a very big idea, yeah.
And we are just scratching the surface here.
We are. We are just getting started.
I'm already feeling my brain stretching in new directions, so I can't wait to delve even deeper into these ideas.
Yeah, me too.
In the next part of our deep dive, stay tuned, listeners, because we've got a lot more ground to cover, including some mind-blowing possibilities for actually manipulating time.
Oh, yeah.
The fate of information in black holes.
Yes.
And maybe even a few clues about dark matter and dark energy.
Buckle up.
All right, we'll see you next time.
Sounds good.
Welcome back, everyone. Last time, we left off on this crazy idea that gravity might not actually be a fundamental force, but rather an emergent property.
Right.
Linked to these entropy gradients and time dilation.
Exactly.
It's like the universe is playing this cosmic game of hot potato with time, and gravity is just the result.
It's a really fascinating way to look at it.
It is. It is.
And it kind of opens up some really tantalizing possibilities.
Yeah, like
imagine if we could manipulate time dilation to create artificial gravity.
Hold on. Artificial gravity. That's straight out of science fiction.
I know, right?
How could we possibly manipulate something as fundamental as time?
Well, the research suggests that if we could control the distribution of entropy, we could potentially influence the flow of time in localized regions.
Okay.
Imagine creating a zone where time flows a little bit slower than its surroundings.
Okay.
Matter would naturally be drawn into that area, much like it's attracted to a massive object.
So instead of needing a giant planet or a black hole to create this gravity well, we could just manipulate entropy to achieve a similar effect.
Exactly. That's the idea. And it could revolutionize space travel.
Oh, wow.
Imagine a spacecraft that doesn't need to carry heavy fuel to propel itself.
Right.
Instead, it could generate its own localized time dilation, essentially falling forward through space-time.
That would be a game changer.
It would, but let's be realistic. I mean, manipulating entropy sounds incredibly complex.
Yeah, even if it is theoretically possible,
Right.
what kind of technology would we even need to do something like that?
Well, that's where things get really speculative. I mean, we're talking about pushing the boundaries of our current understanding of physics.
Right.
But one idea that I found really interesting is harnessing the power of extreme cooling.
Extreme cooling.
Yeah.
Like getting things close to absolute zero.
Exactly.
But how would that help us manipulate time?
Well, remember how temperature is a measure of the average kinetic energy of particles in a system? So at absolute zero, all motion would theoretically stop.
Right.
And if energy and time are linked, as some physicists believe they are, approaching absolute zero could mean slowing down time itself.
Interesting.
It's like creating a thermal event horizon.
Whoa, a thermal event horizon.
Yeah.
That sounds eerily similar to what happens at the edge of a black hole.
Right.
Where time essentially collapses.
Exactly.
Are you suggesting there's a connection between extreme cold and the extreme gravity of a black hole?
It's an intriguing thought, isn't it? It kind of speaks to this interconnectedness
Yeah.
of all these concepts that we're talking about. Entropy, time, temperature, gravity.
They're all kind of woven together.
They're all woven together.
In ways we're only beginning to understand.
Absolutely.
This is really blowing my mind. But before we get too lost in the theoretical weeds here,
okay,
let's go back to black holes and the information paradox.
Okay.
We're about to dive into how information might be preserved even within the singularity of a black hole.
Right, because if information is truly lost inside a black hole, it would contradict this fundamental principle.
Yeah.
That information can't be destroyed.
Right, so let's explore this.
Yeah.
So what are some of the leading ideas out there about how information might escape the clutches of a black hole?
Well, one intriguing possibility is that the information isn't encoded in the Hawking radiation itself, but rather in these very subtle quantum correlations between the particles that make up that radiation.
So the information isn't like a message written on those particles,
right,
but rather hidden in the relationships between them.
Exactly. It's a concept that some people call black hole soft hair.
Black hole soft hair.
Like, it suggests that the information isn't truly lost. It's just incredibly difficult to decipher.
But how would information from the singularity, where time supposedly stops, make its way to the event horizon to even be encoded in those correlations?
That's where quantum entanglement might come in.
Entanglement, right.
Yes. Remember, entanglement allows particles to be linked across vast distances.
Right.
They share this mysterious connection that transcends space and time.
Yeah, entanglement is one of those things in quantum mechanics that just makes you go, what?
I know, it's like two particles having a secret conversation, no matter how far apart they are.
Exactly.
So imagine this. What if the information at the singularity is entangled with particles at the event horizon as the black hole evaporates, and those particles radiate away, the information is carried along with them, encoded in those entangled connections.
So entanglement could be the bridge that allows information to escape a black hole's gravitational prison.
It's certainly a very compelling possibility, and it highlights this incredible potential of quantum mechanics to rewrite our understanding of the cosmos.
It really does. It really does.
But, we've been so focused on black holes that we haven't even touched on how this new perspective could shed light on dark matter and dark energy.
Oh, right. That's right.
We were talking about earlier how those time dilation gradients could explain why matter clumps together to form galaxies.
Yeah.
Could those same gradients explain the mysteries of dark matter and dark energy?
That's a great question.
Right. And that's where things get even wilder.
Okay, let's hear it.
Remember how we talked about time flowing slower in regions of higher order?
Yeah.
Well, what if those vast, seemingly empty regions of space aren't actually empty? But rather regions where time flows much faster due to lower entropy.
So instead of being filled with this mysterious dark matter,
right,
these regions might just be experiencing time differently.
Exactly. It's like they're fast-forwarding through time.
It's like they're on fast forward.
Yeah, while the rest of the universe is in slow motion.
Right.
And because our observations of the universe are so dependent on the flow of time, those regions would appear to have less mass than they actually do.
I see.
This could actually explain those gravitational effects that we attribute to dark matter.
That's really interesting.
Right.
It's like we've been attributing this missing mass to dark matter.
Yeah.
When it might just be a side effect of these time dilation gradients.
Exactly.
Wow. And what about dark energy?
Yeah.
Could that also be explained by this?
Well, if variations in vacuum energy density are responsible for gravity, as some physicists believe, then those same variations could also be driving the accelerated expansion of the universe. It's like the fabric of space-time itself is responding to these quantum fluctuations, creating a kind of cosmic anti-gravity.
So dark energy might not be some mysterious force pushing everything apart,
right,
but rather an emergent property of these entropy gradients and their effect on the vacuum energy.
It could be, yeah.
So we're talking about a universe that's self-regulating.
Potentially, yeah.
Its expansion driven by the interplay between order and chaos.
Exactly.
Energy and time.
And if that's true, it paints a picture of a universe that's even more dynamic and interconnected than we ever imagined.
This is seriously mind-blowing stuff.
I know, right?
We've gone from rethinking gravity to unraveling the mysteries of dark matter and dark energy, all thanks to this connection between entropy and time.
It's pretty amazing.
It is, and I can't wait to see where this rabbit hole leads us next.
Me neither. The journey is far from over.
Welcome back to the deep dive. I feel like we've tumbled down this rabbit hole of cosmic proportions.
It is a deep one.
Exploring this mind-bending connection.
It is.
Between entropy, time, and gravity.
Absolutely.
And honestly, I'm still trying to wrap my head around it all.
It is a lot to take in.
It is.
But that's what makes it so exciting.
It really does. It's a reminder that there's still so much we don't know.
Yeah.
So much more to discover.
Absolutely.
The last time we were grappling with this idea that black holes might not be cosmic information shredders after all.
Yeah.
Instead, information might be encoded in these subtle quantum correlations.
Right.
Thanks to the magic of entanglement.
Yeah, entanglement is amazing.
It is.
It's one of the weirdest things in quantum mechanics, I think.
It really is. But even if that's true, how does that information actually escape the black hole's grip?
Right, because it can't just beam itself out, right?
Right, exactly. So
yeah.
What are some of the ideas out there about how information might make its grand exit?
Yeah.
From a black hole.
So one possibility is that as the black hole evaporates, the information is slowly transferred to the outgoing Hawking radiation.
Okay.
But not in the particles themselves,
right.
but in the subtle correlations between them.
Okay, so it's not like each particle carries a little piece of the information, but rather the information is spread out across this whole network.
Exactly, yeah.
Of correlation.
Yeah, it's a concept that challenges how we normally think about information storage and retrieval.
It really does.
But it's something that people are seriously considering within quantum information theory.
So it's mind-boggling to think that something as seemingly destructive as a black hole
I know, right?
could actually be preserving information in such a complex and subtle way.
Yeah.
But even if information can escape, there's still this puzzle of how it gets from the singularity, where time supposedly stands still, to the event horizon, where it can be encoded in those correlations.
Right, and that is a key piece of the puzzle.
Yeah.
And quantum entanglement might play a role there, too.
Okay.
So remember those entangled particles?
Yes.
Imagine particles at the singularity.
Okay.
Entangled with particles at the event horizon.
Okay.
As a black hole slowly evaporates, the entangled particles at the event horizon radiate away.
Right.
And they carry that information with them, encoded in those quantum connections.
So entanglement could be this secret tunnel.
A secret tunnel, yeah.
That allows information to escape the black hole's clutches.
Right.
Bridging the gap between the singularity and the outside world.
Exactly.
It's like a cosmic game of telephone.
Yeah, a cosmic game of telephone.
With these quantum whispers carrying messages across the abyss.
I love that. That's a great analogy.
It's a beautiful and mind-bending concept. And it speaks to the power of quantum mechanics to resolve some of the biggest mysteries in the universe.
Absolutely.
But let's not forget about these other mysteries we've been talking about.
Okay.
We've explored how these time dilation gradients could explain the formation of galaxies.
Yeah.
But what about dark matter and dark energy?
Right. Could they also be pieces of this cosmic puzzle?
Could they?
There is a growing body of research exploring those connections.
Okay.
Remember how we discussed the possibility that those vast, seemingly empty regions of space might actually be regions where time flows much faster?
Right, it's like those regions are on fast forward.
Fast forward.
Where the rest of the universe is playing in slow motion.
Yeah, exactly. Yeah. And because our observations of the universe are so dependent on the flow of time, those regions would appear to have less mass than they actually do. And that could account for those gravitational effects that we attribute to dark matter.
So instead of invoking some mysterious, invisible substance, we might be able to explain dark matter as a side effect of these time dilation gradients.
Exactly. It's a radical idea.
It is.
But it's gaining traction among some physicists.
That's really interesting.
And if it turns out to be true, it would completely revolutionize our understanding of the universe's composition and evolution.
Incredible. And what about dark energy? Could that also be explained by this new perspective?
Well, if variations in vacuum energy density are responsible for gravity, as some physicists believe, then those same variations could also be driving the accelerated expansion of the universe.
So instead of being some mysterious force pushing everything apart, dark energy could be another emergent property of this dance. Between entropy, time, and gravity.
That's one of the ideas that's out there.
Wow, so we're talking about a universe that's self-regulating.
Yeah.
Its expansion driven by this interplay of order and chaos, energy and time.
Exactly. It's a beautiful picture, isn't it?
It really is. It's amazing to think that all these seemingly disparate phenomena, from the formation of galaxies to the expansion of the universe itself, could be interconnected through this fundamental relationship between entropy and time.
Yeah.
It's like we've uncovered this hidden code, this deeper language of the cosmos.
I love that, a deeper language of the cosmos. Yeah.
It really is. It's fascinating.
It is.
It's an incredible journey.
It is.
This deep dive.
A deep dive, indeed.
Into the very heart of reality.
Yeah.
We've challenged our assumptions.
Yeah.
Explored these mind-bending possibilities.
Yeah.
And glimpsed a universe that's far more complex and interconnected than we ever imagined.
Absolutely. And who knows what other wonders await us as we continue to explore this frontier.
Well, we'll leave you with that thought-provoking note.
Yeah.
Until next time, keep those minds open.
Keep them open.
And those questions flowing.
Farewell, fellow explorers. May your curiosity always lead you to new and exciting discoveries. Journey 93